So like we were saying before, 1, 2, and 3 are dependent, independent, and independent.
Yeah.
Number 4, Seth draws a colored tile from a bag, replaces it. Draws a second tile from the bag, replaces it, and then draws a third tile from the bag. Are these independent or dependent events? Yeah. Why? Oh. Yes. Yeah. So, does it matter whether or not you replace it on the third time? Is there an event happening after? You're right. If it didn't say replaces it, right. If it didn't say replaces it and then there was a fourth event, you're right. That would be dependent. But because we are replacing each time, is it independent or dependent? Independent. Good. So that's an I. You draw a red marble from a bag and then another red marble without replacing the first marble. Dependent. Good. Why dependent? Yeah, you're not replacing it. You're changing the total on the second event. So after doing this 1 through 5, what do you think determines independent?
Replacement.
That keyword of replacement. So up at the top, I want you to write independent. And what makes two events independent, a good keyword is with replacement. With replacement. And then dependent, a good keyword would be no replacement. Independent and dependent. Now, the only reason you need to differentiate between independent and dependent is because when you are dealing with multiple events and it is dependent, each time you're finding the probability, what's going to happen to the total? If I don't replace something, what will happen to the total? It goes down each time. Good. So let's try to practice finding compound probability, remembering about independent and dependent. So here we have a compound probability of spinning 2 spinners. Are these independent or dependent events? Independent, right? If I spin a D on this first spin, it has nothing to do with the second spin when I'm spinning the numbers. So we know it has nothing to do with each other. We do not need to subtract the totals. Over here, it wants us on number 6 to find the probability of spinning an A and a 2. In the past, to find this probability, I told you, draw a tree diagram, right? Well, there is an easier way. What would be the probability of spinning an A on this first spinner? 1/4. So I'm going to put a little 1/4 here. And what's the probability of spinning? It wants now a 2, I think. It's very blurry. Yes, a 2. What's the probability of spinning a 2 on the second spinner?
2 out of 6.
Yeah, 2 out of 6, or simplified to 1/3. Yeah, there are 2 2s there. Whenever you see the word and between 2 events, so it wants to know the probability of A and 2, you should immediately think you need to multiply the probabilities. And is multiplication. And then later on, we'll get to or. Or is add. So I know it's backwards from what you think. You would think and is addition. In probability, it's not. When you're trying to find the probability of A and 2, you multiply. So here we're going to multiply these 2 probabilities. How do I multiply fractions? Yes? That's when you're dividing fractions. Ooh. That is when two fractions are set equal to each other. Yes. That is when you're adding or subtracting fractions. I think, Morning? Perfect. You're just multiplying straight. So 1 times 1 is 1. What is 4 times 3? 12. That's our probability. So now we'll try it a couple more times and then you'll do it. What's the probability of spinning a D? 1/4. And what's the probability of spinning a 1? 3 out of 6 or 1/2. Good. And what do we do if it says and between those two probabilities? Multiply. And we multiply the numerators and the denominators. So what's 1 times 1? And 4 times 2. So our probability this time is 1/8. And what about the probability of B? Again, 1/4 and 3. 1/6 this time. 1 times 1 is 1. 4 times 6 is 24. So we have a 1 out of 24 chance of spinning a B in 3. And what about A? We know it's 1/4 again, and not 2. Everything but 2's, right? So it's what? 4 out of 6 or 2/3, which is 2 out of 12, which simplifies to beautiful. Any questions on these compound probabilities? I think I want to go over one more, because what is different about this next section? You're not replacing, meaning the total is going to do what? Go down each time, right? So it says a box contains 3 marbles, 3 red marbles, 6 blue marbles, and 1 white marble. The marbles are selected at random, one at a time, and are not replaced. So we want to find the probability of first pulling a blue, then a red. What is the probability of pulling a blue? 6 out of 10. And now I do not replace that 1 blue marble I took. How many total do I have left? 9. It's not the total number of red. I wouldn't put a 3 here. It's the total marbles. And how many red do I have that I put up top? So 6 times 3. Yes. Yes, all of those. 10. But remember, on this first probability, I took out a blue. So now there are only 9 in the bag. That's why I went down to 9 here. And what does 18 over 90 simplify to? Perfect. Any questions on how to do these problems? I had one girl think that each one of these problems, you're continuing subtracting the total, so the next one would be 8. No, treat each one of these as a separate problem. So you're starting back up at 10 as the total. All right, you guys go ahead and finish the front of this page. So now we're going to be going over Venn diagrams and how they relate to the probabilities we've been doing. Suppose we are selecting a student at random from Round Rock High School. Let A be the event that the student takes art and B be the event that the student takes basketball. So here we have these Venn diagrams. A represents our art students and B our basketball students. It wants us to shade the region representing the event that the selected student takes in art class and plays basketball. So what do you think the keyword there is? And. Perfect. What section of this Venn diagram do you think this represents? Where they intersect. And actually, in probability, another word for and is the intersection. So let me write our probability notation for and. So up until this point, you've just been probably writing the probability of A and B. Well, there's actually a symbol for and or intersection, and it is an upside down U.
Really?
This reads the probability of A and B. It's just a symbol. So this is the symbol for and, or we can also call it the intersection. And what do we do when we're trying to find the probabilities with and between them? Multiply. Multiply. So next, it says shade the region representing the event that the selected student takes an art class or plays basketball. So where do you think this section is going to be? So let's ask ourselves, this part of A right over here, do those students take art or basketball? Yeah, so we know we're going to shade there. What about here? Do they take art or basketball? What about here? Do they take art or basketball? Yes. They just happen to also take both. Doesn't matter. They still take art or basketball. So we are actually shading everything inside the circles. Now, this is the or as it's sometimes called the union between A and B. So our probability notation is the exact opposite of and with a U. This is the symbol for or the union of A and B. Now, as you may or may not know, we are just barely brushing the surface of probability. I took a whole college level course on probability. We are barely skimming that. There is a whole lot more to or that we just do not have time to teach. Or is a lot more complex than and I'll show you why it's easier to see when we look at the table down below. So just keep in mind there's more to or. Next, it says shade the region representing the event that the selected student does not take art. So this is the portion that is not circle A. Where do you think I'm going to shade? All of B? Which part of B? The part that is not included in A, right? So just this kind of crescent shape we have going here. Now, are there students at our school that do not take basketball or art? Yeah, there are. Where do you think those students are represented in this Venn diagram? They are in the outside area. So do these students not take art? They don't. So when we're thinking about not art, we not only need to include this crescent shape of B, we also need to include the surrounding area. Literally, it's everything except circle A.
What about the middle?
The middle is still part of circle A, so I can't shade that. Because those students do still take art. Now, another word for not is the complement of A, right? So in this picture, circle A and not A complement each other because wherever A isn't, the not space happens to be. They are called complements of each other. That is why in our probability notation for not, So the probability of not A is a capital A with a C as an exponent. And that C stands for complement. Any questions so far? All right. So now we're going to look at this table to understand the differences between and, or, and not a little bit better. A store has 48 different phones available with or without caller ID and with or without a speakerphone. If a phone is chosen at random, what is the probability that the phone has a speakerphone and caller ID? So let's look at this table. What number do you think depicts caller ID and speakerphone, or the intersection between those two? What is it? So we want speakerphone and we want caller ID. Where do these two columns and rows intersect?
At 18.
Oh, at 18. That's our and between caller ID and speakerphone. 18 out of, what's our total? 48. Now, I'm going to write my probability notation, and I'm just going to simplify these words down to S. And then what's my symbol for and? Yeah, it kind of looks like an N, right? That's kind of how I remember it, is it looks like an upside down N, and there's an N in and. So speakerphone and caller ID, or I'll just say ID, is equal to 18 over 48. And can that be simplified? Down to 3/8. So now, speakerphone but does not have caller ID. So before we find this probability, do you think it's and or here? Is it going to be the intersection or the union? It's and. Speakerphone but does not have caller ID. It still wants both of these things, doesn't it? You can't just have speakerphone because that doesn't include the not caller ID. Even though it doesn't literally say the word and, you should think about it and understand that it still wants both of these things to happen at the same time. So we want speakerphone and no caller ID. So where's the intersection between those two? At 16. And our notation, P, S, and it's still and, so we put the upside down U, but no caller ID. So this time I'm going to put ID with a what next to it, you think? A C. Good. And that is 16 over 48, which simplifies to 1/3. Now here's my favorite part. I happen to love or. We want to find the probability of speakerphone or has caller ID. So do both of these things have to happen? No, just one of them, right? That's the difference between or and. That's why it's no longer the intersection. So if I want all of speakerphone, I want everything that could happen in a speakerphone, it's going to be this entire column here. And then I also want to include caller ID. So it includes this entire row. What would you think is my probability of a speakerphone or caller ID? Ooh, We've got some bright thinkers in here. Why 36?
Because this is already told for speakerphone and caller ID, or no speakerphone caller ID, and yeah, just added to the 6.
Right. So a common mistake would be to say, oh, it's 54 out of 48. What did I do wrong?
You added the caller ID, speakerphone, and no speaker.
So when I say 34 plus 20 and get 54, what am I actually including twice? I'm including the intersection. So this is why OR is kind of tricky. There is an equation way to do it, but again, we don't have time for me to teach you that. So instead, whenever you're dealing with OR, I'm going to tell you draw a table or a tree diagram. We just do not have time for me to show you the equation. So instead of it being 54 over 48, it is instead 34 plus 2, which is 36. So the probability of speakerphone or caller ID is 36 over 48, which simplifies to 3/4. Perfect. Any questions here? All right, I do want to get you started on the back. So I'm going to help you out to begin with here. So it says the most popular color for a vehicle is white. So we know, well, that's just leading information. The most popular color for a vehicle is white. Suppose that a vehicle is selected at random from a city, and let C be the event. There should be a T there. The event that the vehicle is a car. So C stands for car. And W be the event that the vehicle is white. So W stands for white. Write your answer in probability notation. So looking at this Venn diagram, what do you think those decimals represent? Right, they literally represent the probability of those events occurring. Sometimes you will see Venn diagrams where it just gives you like numbers of cars and numbers of cars that are white, and you have to compute the probability. But they started you off easy here and just gave you the probability right off the bat. It says, what is the probability that the selected vehicle is a car? So P, the probability that is a car, is equal to, what do we do here?
62%.
Well, so we want the entire circle of car, right? Is 60.62 the only number inside our car circle? What is also another number there? 0.14. So what do you think we need to do to those? Yeah, just add them together. They already found the probability, so I do not need to multiply here. They already found the probabilities. I'm not multiplying. All I'm doing is just combining these. So 0.62 plus 0.14 gives us, or 76%. Does this make sense to everybody? All right, and I would like for you to add one more to the bottom, part F. Find the probability that the vehicle is not white. So I want you to complete parts B through F and then work on example number 2.